Okay, so the next step is solving the discrete model. So let's suppose that we have used one of the methods that takes our continuous equations and turns them into discrete equations, and now we need to solve them. So we go to solve them, and for certain classes of things, often actually like a really easy heat transfer problem, that where you're just solving like the Laplace equation, often you can use direct linear algebraic solvers to get those. And in that case, you'll be able to get the discrete solutions like very fast. And because they'll be doing, essentially Gauss elimination or LU decomposition, they'll find the exact solutions, and you won't have to worry too much about user choice in that process. But many big simulations can't actually use direct solutions. Like Gauss elimination actually requires a lot of memory if you have a full matrix. And so that process can actually be so intensive that you actually have to use iterative solvers to get them, like the conjugate gradient method, let's say. In addition, if you have a nonlinear problem, all nonlinear problems require iterative solvers. So you're probably familiar with one type of nonlinear solver. So like the Newton's method, where you use the local slope of the solution to guess a new solution. And then you basically keep iterating until you actually zoom in on like a zero crossing, for example, in an algebraic equation. So Newton's method is a method you use to iterate to solve a single algebraic equation. The Newton-Raphson method is like the multi-dimensional analog of that. If you have a large system of nonlinear equations, you will have to iterate to get the solution. And a part of that process is deciding when to stop. So you will never get the exact solution when you use an iterative solver, because you'd have to iterate an infinite number of times. But so generally you'll iterate a finite number of times, and you will have to decide when to stop. When is it good enough? And so making that decision is part of that process too. It's a user choice. Okay, so actually, even though we didn't use the finite element method, we encountered this problem recently. So in the flash diffusivity exercise, you got a so-called analytic solution to the problem, so an infinite series solution. But it turns out if you want to like numerically evaluate an infinite series solution, well, you can't like take an infinite number of sums. So you cut it off at some point, right? So you took a certain number of terms in the sum, and after you took enough, you gave up. So like typically there's a user choice about how to stop that, and the choice really comes down to how accurate or how many significant digits do you want to have when you're done. So a typical way to do this is to look at the next value of the sum and see whether it is a significant change from the previous value of the sum. And if it's not, then stop. So like, for example, that kind of thing is involved in the solving process. So choosing which type of solver to use when you have a choice is also part of that simulation process.